Hello students, welcome to Physics Wallah, Gate Wallah. How are you? So I hope your preparation is going absolutely fine. And very warm welcome in this series of basic thermodynamics. And in previous lectures, we already completed the basic definition part of basic thermodynamics. So up to now, we had covered that what is thermodynamics, how to study it, what method we are going to use to study it, and what is a condition to use that, concept of continuum we discuss. And after that, what is system, surrounding, boundary, right, thermodynamic properties, process, state, cycle, and thermodynamic equilibrium. Each and everything we discuss in much detailed manner, and I'm hoping that you have already covered those things and you understand each and every concept in detailed way. Now now we are going to slowly enter into the subject. Up to now, whatever we discussed, that is a very basic part, and most of you are aware of it, right? Most of you are already comfortable in those particular areas. Now we are slowly entering into the thermodynamics. But if you are studying this subject first time, then it is my suggestion to watch the previous lectures also, right? Then only you will get the command in this particular subject. Sometime I seen that students are thinking that, sir, question is coming from first law, question is coming from second law, entropy and all, why to study this one? Rarely questions are coming from these areas. But these things are completely linked. If you are not thorough with the basic definitions and all, then you will not able to solve the problem of first law, entropy, or second law, right? So you must be thorough in those areas. Okay. So today we are going to start our discussion on the properties of the ideal gas. Now your question is, sir, why we are studying this? As I told you at the very first day of this series, that is, a thermodynamics is the branch of science that deal with the heat and work interaction and its effect on the properties of the system. Now, properties of the system. Now, what can be the system? System can be either control mass or control volume. That also we discussed. But what will be there? Basically, right? It will be some substance, obviously, right? Suppose turbine is there, is an open system, but obviously some substance is going to be flow. Suppose piston cylinder arrangement is there, it is a closed system, but inside the piston cylinder arrangement something will be there, no? That is basically our system. So in most of the cases of thermodynamics, our system is basically gases. Sir, why gases only? Why not solid, and why not liquid? No, it can be a system. Thermodynamics is applicable everywhere, right? Every single place, wherever temperature is there, thermodynamics is there. So obviously the laws which we are going to study in future, that is basically going to use for everywhere. It's maybe solid, it may be liquid, it may be anything, right? But when we are coming to the classical thermodynamics, where the aim of subject is to convert the non-organized form of energy, means heat, into the organized form of energy, that is work, then to get work from a particular system, generally we are getting work due to expansion, whether it's a closed system or open system. You may have seen that IC engines are there, right? So here piston is expanding and we are getting work, correct? Same thing is happening in turbine also. In turbine, the steam is going to be expand and we are getting work. So basically we are getting work due to the expansion, means increasing the volume, right? Now if suppose you are talking about solid or liquid, then solid and liquids are treated as incompressible, means their volume is not going to be changed. So obviously to fulfill this particular requirement of getting work from a particular system, the working substance should be in such a way that it should expand, right? And expansion means gas, right? So generally our working fluid in most of the application of thermodynamics are gases only. Yeah, it is true that the laws, whatever concepts, these are applicable every single places, solid also, liquid also, but in most of the cases, whether it's a IC engine or gas turbine or steam power plant or refrigeration related things, everywhere the working fluid is basically gas. So we must know what are the properties of the gas, then only we will able to use those properties to analyze the system. Clear, right? So In this lecture we are going to talk about the properties of gases, and not gases, basically ideal gases. Okay, real gases also will discuss, what are the constitution, what are the things involved in the real gases, that also will discuss, don't worry, right? But first we are going to talk about the ideal gases. Even in our real systems also, whatever gases are used, right? Let's say gas turbine is there, or IC engine is there, we are using air or air fuel mixture or something, right? So that is actually treated as ideal gas. So these gases can be considered as ideal gas. What is the criteria, that I'll tell you. Okay, in a steam power plant, in every situation you cannot treat it as ideal gas, but in this particular portion, like in gas turbine, IC engines, working fluid is ideal gas. Even in steam engine also, right, or steam power plants also, in majority of the portion you can consider steam as ideal gas. In some cases you cannot, but in most of the cases you can consider it as ideal gas. So basically you must know what are the properties of the basic properties of the ideal gas. So in today's lecture we are going to talk about the basic properties of the ideal gas. In next lecture we will talk about the advanced properties of ideal gas, or what is the relation, or what is the differences in ideal gas and real gas, what is a van der Waals gas, what is the other type of gas, what is the compressibility factor. So all the advanced things we'll discuss in the next lecture basically. So today we are going to talk about the basic properties of the ideal gas, but you must be thorough with the basic properties, because if you are not good in basic properties, then how can you imagine to learn the advanced properties? Correct na? Right. So let's talk about the basic properties. So the very first question is coming here, that what is ideal gas? What is ideal gas? So in 1662 Robert Boyle was doing one experiment at very low pressure, means in vacuum he was doing one experiment, right? And then he found something, right? What he found, that if we are maintaining the temperature constant, he was maintaining the temperature constant, then what he found, that pressure is inversely proportional to the volume. Means he found that pressure is inversely proportional to the specific volume at constant temperature, right? At constant temperature is constant, all right? Okay, or even you can write this as a P into V is proportional to, or P on V is equal to constant, you can write is equals to constant at T is equal to constant. It means that in this constant basically temperature term can be there. This is the law, basically the first gas law given by the Robert Boyle, and this was applicable at a vacuum condition. It was applicable at vacuum. What is the significance of this word vacuum? You will understand very soon. Now after approximately 100 years, after Boyle's approximately after 100 years, means in 1787, right? 1787, J. Charles, up to these 100 years approximately, only one law was there, right? And that is basically gas law. People call it as a gas law, right? Now then one more thing is coming in 1787, that J. Charles and Gay Lussac, they were also doing some experiment, and they finally found two basic statements. The very first statement was that at very low and constant pressure, a specific volume is proportional to the temperature. Means a specific volume is proportional to the temperature at P is equal to constant. And if we are maintaining a specific volume as a constant, in that case P is proportional to the temperature, means P is proportional to the temperature at V is equal to constant. So basically you can see that there is three equations. There is a first equation, there is a second equation, there is a third equation. So basically we have three equations here, right? Three equations are there. So you can say that any gas, if any gas is following all these three equations, correct, at all pressure, temperature and volume, then we can call it as an ideal gas. But like it's not convenient, no? that to check all these three laws. So what we are going to do, we are going to combine these three equations. We are going to combine these three equations. So obviously you can see that by seeing itself you can conclude one thing, that if volume is constant, like if pressure is constant, volume is proportional to the temperature, means here temperature must be there. Here temperature must be there. Similarly here also, that if volume is become constant, pressure is proportional to temperature. So in this term temperature should be there. So I can say that PV is proportional to temperature. PV is proportional to temperature, or we can say PV equals to some constant into T. PV is equal to RT. That constant is called as characteristic gas constant, RT. So basically we can say that if we combined all these three, then we can get here PV is equal to RT, right? This is R is a characteristic gas constant. Now further you can write, like if you multiply mass both the side, then P into V capital V, M into small v is capital V, means total volume is a specific volume, MRT, correct hai? This is the ideal gas equation. This is basically what ideal gas equation. Even one more form is possible. You can write like this also, that P is equal to M by V RT. Now M by V is what? Mass per unit volume is density. So you can write P is equal to rho RT. That is also ideal gas only. This is ideal gas equation only, right? So this is one form of equation. This is another form of equation. Now what is P here? Mostly students are saying that, sir, P is a pressure. No, always remember it is a absolute pressure. P is what? P is basically absolute pressure. Never ever forget it. Never ever forget absolute pressure. And the unit is kilopascal. Sir, why kilopascal only? We can put here Pascal also in an SI system. We are dealing with the SI system, so we can put here Pascal also. Yes, you can put Pascal, no problem. But generally Pascal is a very small unit of pressure. So whatever units are generally given in the question, that is in form of Pascal, and R values also defined for kilojoule per kg Kelvin actually, right? So it is convenient to remember as a kilopascal. Always try to put this value in kilopascal. 99.9% cases of the problem, they will give you the value of pressure in kilopascal only, because Pascal is very, very small. Okay. Then V is what? V is basically volume. Volume is in meter cube obviously. Then mass is, M is mass, that is obviously in kg, right? And T, what is T here? T is again absolute temperature. Never ever put the value of temperature in degree centigrade or Rankine or anything else. Always you have to put value in Kelvin, because only there is number of temperature scales, but only one absolute scale, that is Kelvin scale basically. Then this R is called as what? Characteristic gas constant. Characteristic gas constant. Sometimes people call it as gas constant also. Sometimes it is written as a simply gas constant also. Correct? So, but there is two different type of gas constant. One is characteristic gas constant. One is universal gas constant. So basically we are discussing both, right? Both is important for us. That's why we are putting it as a characteristic gas constant, but you can identify both of them with the help of units. Here unit will be kilojoule per kg Kelvin. Kilojoule per kg Kelvin. Okay. Kilojoule per kg per Kelvin. Okay. So these are the basically things given to you. So now this is a very basic equation for ideal gas. So now onwards, if someone will asking you that what is ideal gas? So you can say that a gas which obeys ideal gas equation means PV is equal to MRT or PV is equal to rho RT at all pressure, temperature and volume is called as what? Ideal gas. Now one more term is defined here, that is known as what? Number of moles. Please listen here carefully. Number of moles. Number of moles. Number of moles. As we all know, that mole is also a fundamental unit, right? Quantity of a substance. So mole is there, right? Number of moles. So number of moles is basically what? Number of moles is small n, is defined as the mass small m by molecular weight. Molecular weight, that is capital M. obviously, right? Suppose total mass, whatever mass is there in your room, that is nothing but equals to 1 mole. You just take the 1 mole into total number of moles into the weight of the one molecule, 1 mole basically, right? So if you multiply that, you will get the total mass. So basically you can write here m is equal to n into capital M. What you can write? M is equal to n into capital M, right? Now if you put this value here, then you will get PV is equal to n capital M RT. PV is equal to n capital M RT. So PV is equal to n m cap right RT. Now here one scientist is coming in our picture. That name is Avogadro. As per Avogadro hypothesis, for any gas, whatever gas it may be, if it have a fixed pressure, temperature and volume, then number of moles for each gas is going to be same. Means at a particular pressure, temperature and volume, means in particular container, suppose you are maintaining same pressure, temperature and volume, then whatever gas it may be, number of moles are going to be fixed only. Means I can say that if pressure, temperature, volume is fixed, then n is also fixed in that for any gas. It means that m into r will also be fixed. If all other are constant, then m into r is also constant. So we can say that by Avogadro hypothesis. By Avogadro hypothesis, we can say that m into r is equal to r bar. M into r is equal to r bar. Just put this value here. This is a constant. This is called as what? Universal gas constant. Universal gas constant. Gas constant, right? Its value is basically what? R bar value is 8.314 kilojoule per kilomole Kelvin. Always remember. So the characteristic gas constant kilojoule per kg Kelvin. This is defined per mole. This is defined per mass. So just put this value here. So you will get PV is equal to n r bar T. PV is equal to n r bar T. This is another form of ideal gas equation only. This is another form of ideal. So basically we have 3 different form of ideal gas equation, but 2 are fundamental. One is this one. This is a mass basis. This is mass basis. This is molar basis. Clear hai? So I hope up to here there is no any problem. So here I can write m is equal to n into capital M. Then we can write here PV is equal to MRT. In place of M we can write PV is equal to N capital M R T. So this is the Avogadro hypothesis. So as per Avogadro hypothesis, M into R is equal to R bar. So we can write PV is equal to N R bar T, where R bar is equal to 8.314 kilojoule per kilomole Kelvin. You know, one question was asked earlier, right? One question was asked earlier, very basic question was there, and in which you need to calculate the m value, right? In which you need to calculate the value of mass. Mass ka value nikalna tha, right? So to calculate the value of mass, we need to use PV is equal to MRT. PV is equal to MRT. But the problem is some of the students left that question. They simply came to me and said that sir, question was wrong. I said why? Because sir, we need to use PV is equal to MRT to calculate M. But unfortunately the R value was not given. So I said you should remember this. So sir, I remember R value of air, standard value, but it was CO2. So how can I remember the value of all the substance? I said you need not to remember all the values. You can calculate the value basically, right? You can calculate the value basically. How you can calculate? Very simple. How can you calculate? Very simple. See, suppose R of air you need to calculate. So R of air value will come how much? R bar by capital M of air. Simply just put the value 8.314 divided by molecular weight of air is 29. So this value will come 0.287 kilojoule per kg Kelvin. Similarly, let's say R of argon or R of CO2, for example, you need to find out. Then this value will come R bar by capital M of CO2. So this value will come 8.314 divided by 44. So this value will come 0.188 something like that kilojoule per kg Kelvin. You are get clear? Hai? So you can calculate the R value like this. You can calculate the R value like this. Is it clear to everyone? All right. Now, now one more thing I would like to share here, that for ideal gas few more very basic equations are there that I want to share here. For ideal gas we can write here, for ideal gas Cp minus Cv is equal to R. Cp minus Cv is equal to R. This is basically Mayer's equation and we will prove it, don't worry. We will definitely we will prove this equation right after first law of thermodynamics. After first law of thermodynamics we will prove it, don't worry. So Cp minus Cv is equal to R. And one more thing, that is adiabatic index. Maybe hopefully you all may know about it. Even if you don't know, don't worry. Right, later on we will get to know that the ideal gas equation for reversible adiabatic process PV to the power gamma is equal to constant. This is basically what ideal gas equation for reversible adiabatic process. We will prove it, where gamma is basically adiabatic index. What is that? Adiabatic index is what? Gamma, that is Cp by Cv. Right, it is actually defined, this is macroscopically defined, and microscopically if you see, then gamma is basically defined as a 1 plus 2 by n. N is the and we will discuss in detail. Basically n is a degree of freedom of a molecules. So on the basis of this formula, this lower one, this one microscopic one, we can find out the value of gamma for example monoatomic gases. For monoatomic gases, monoatomic gases means monatomic where only one atom is there, like example is like helium is there, only one is there, helium, argon, etc. For this, value of gamma is basically 1.67. How this 1.67 is coming and all we'll discuss when we discuss about first law of thermodynamics. Then another one is diatomic gases. Diatomic, like where two are there, like example is like O2 is there, O2 here, 2 is there, right? O2 is there, N2 is there, even air is also there. Why air is a diatomic? Because air is majorly a mixture of O2 and N2 only. So the mixture of two diatomic gas is also treated as a diatomic. Then another one is triatomic or polyatomic. Triatomic or polyatomic. So this is example is what, like CO2 or SO2 or etc. N2O. So these are the triatomic or polyatomic gases. For this, okay, sorry, I forget to write here. Gamma is equal to 1.4 and for this gamma is equal to 1.33. Okay, so these are the values of gamma for different gases. Now what we are going to do here, basically, just put the value of Cp from here to here. Means Cp, in place of Cp, what we can write here? Gamma times of Cv. And if I put this value here, then I can write gamma times of Cv minus Cv is equal to R. So I can write Cv is equal to R by gamma minus 1. Right, even R can be written as R bar by M into gamma minus 1. Clear hai? So this is the value of Cv. Similarly, we can find out the value of Cp. Cp is equal to what? Gamma times of Cv. Right, gamma times of Cv. So Cp can be written as gamma R bar by M into gamma minus 1. Right. Now in some of the question I have seen that the Cp and Cv value is also not given. So for ideal gas, Cp and Cv value you can calculate by your own. Cp and Cv value you can calculate by your own. For example, we are calculating the value of CV and CP for air, for example. So CV value of for air, how much you can write? That is R bar by capital M into gamma minus 1, right? So what will be the value? 8.314 divided by molecular weight is 29, gamma value is 1.4 for air, 1.4 minus 1. So this value will come 0.718 kilojoule per kg Kelvin. Kilojoule per kg Kelvin. Now similarly I can write Cp of air. Cp of air value will come how much? R bar by, or directly I can write gamma times of CV, no problem. Gamma times of CV. This value will come 1.4 into 0.718. So this can be written as 1.005 kilojoule per kg Kelvin. Clear hai? I hope it is clear to you. Now if I please listen here carefully. Now if I basically find out some other values like CV value of, for example, I am calculating CV value of CV value of anything like, okay, argon for example. So CV value of argon will come how much? That is R bar 8.314 divided by molecular weight 40, 1.67 minus 1. You just try to solve this. So I also don't remember, I need to calculate this value. So 8.314 divided by 40 divided by 0.67. So this value will come 0.31 kilojoule per kg Kelvin. Now if I calculate the Cp value of argon, then it will be gamma times of Cv value of argon. So just multiply with gamma means into 1.67. इस जगह 0.518 किलोजूल पर kg Kelvin. Clear है? Is it clear to everyone? So basically this is all about the basic properties. So up to now what we already studied, that what is ideal gas, means any gas which obeys ideal gas equation is PV is equal to MRT at all pressure, temperature and volume, that is called as ideal gas, right? And this ideal gas equation can be written in another form, molar basis, that is PV is equal to N R bar T, correct? And we can calculate the value of characteristic gas constant with the help of molecular weight, as well as we can calculate the value of Cp and Cv. Cp, Cv means specific heat. Cv is what? Cp is specific heat at constant pressure, Cv is specific heat at constant volume, correct? So these are the things. Maybe I can understand you may have some, some confusion here. You may even some people may have confusion that what is a specific heat. Even okay, that is a standard thing. That is a different thing. But sometime maybe some of you may forget this. So don't worry about it. For time being, just write all these things on in your notes. Right. When we'll enter into the first law of thermodynamics, then each and every point will come again. What is exactly meaning of Cp, Cv? Which one is more? Why it is always equals to R? Why this value is always positive? Right. Then what is gamma? What is this N? Right. How this value 1.67 is coming? So all these details we will discuss. Don't worry about it. Right. Just for time being, you just note it down. Right. Why? Because whatever we are discussing, whatever we are going to start discussing, right, that is a major our discussion is the what is the concept of this ideal gas. Now up to now we only seen the mathematical form of basically ideal gas. We don't know what is the physical meaning of ideal gas. So in next class we will discuss about what is the physical meaning of ideal gas, right? Can we prove this equation PV is equal to MRT with some other method? Okay, law is there. So obviously there is one theory called as kinetic gas theory. Then what are the assumptions we need to take, right? What is the difference in real gas and ideal gas? In real gas, what type of gases are there, like van der Waals and all? Then how to characterize the real gases with the help of compressibility factor, correct? So all those things we will discuss in next class. So let's meet in next class. Thank you very much.